On the 20th of July, a rock the size of a truck passed Earth. It missed us by 970,000 kilometers, moving near 8 kilometers a second. We found it only 4 days before it arrived, and then it was gone. It did not travel alone through the dark that week around our planet. 5 separate asteroids swept past Earth between the 19th and the 23rd of July. 3 of those 5 were discovered only days before they crossed our path. Not one of them could have harmed you, and I will keep saying so. So here is the question that should hold you for the next 2 hours. If we saw these rocks this late, what about the ones we never see? If a question like that grips you, subscribe now and say where you are watching from. Hold on to it tightly, because everything tonight bends back toward it, so let's get into it. Part 1. The rock we found 4 days too late. Let me rebuild that first rock as a real object moving through real space. Astronomers gave it a name that barely sounds like 1/2026 OY. It belongs to a family called the Apollo asteroids, which cross the orbit of Earth. It circles the Sun once every 616 days or so. At its farthest it drifts out past Mars, and at its nearest it slips inside our lane. For almost all of that journey, no telescope on Earth can see it at all. The rock is simply too faint, too dark, and too small to catch light. Its brightness only rises enough to detect in the final stretch before a pass. From that brightness, and a guess about its surface, we can estimate its size. It measures somewhere between 5 and 11 meters across, about the length of a small bus. A rock that size sits near the bottom of the scale of planetary threats. If it entered our air, it would most likely flare bright and break apart high up. It would put on a spectacular light show, and little of it would reach ground. So I did not open with this rock because of the damage it could do. I opened with it because of the single most unsettling fact attached to it. We did not see it coming until it was very nearly here at all. The first measurements that pinned its path arrived on the 16th of July. Its closest approach came on the 20th, just 4 short days later, at night. The formal circular that gave it a name went out on the 21st. In plain terms, we finished the paperwork after the rock had already gone by. Stay with me, because that timeline is the whole engine of tonight's story. This was not a failure by anyone whose job is watching the sky. Rocks this small stay invisible until they are almost upon us, and that is physics. The point here is harder than blame, and it runs like this. For an entire class of object, a few days of warning is the best we have. Now let me put that missed distance into something your body can actually feel. The Moon sits about 384,000 kilometers from Earth on average. This particular rock passed at roughly 970,000 kilometers from us. That means it crossed at about 2.5 times the distance to the Moon. In the scale of the whole solar system, that is a genuine near miss. In human terms, though, it was a comfortable and complete miss, and both are true. Holding those two truths at once is the entire skill this subject demands of you. Panic lives in forgetting the second truth, and denial lives in forgetting the first. I am going to ask you to hold both of them over and over tonight, because the rock that misses is never once the real story here, as you will see. Here is what makes 2026 OY worth your time, despite being harmless. It was not a lonely visitor that happened to wander close to our world. It was the nearest member of a small crowd passing in the same nights. 5 rocks in 5 nights is not, by itself, a headline worth panic. But that crowd draws a picture of our situation no single rock could draw. Let me say a little more about how faint this rock truly was. Its brightness sat at a value astronomers write as roughly 28.6. To your eye, that is fainter than a candle seen from thousands of kilometers away. A rock like that reflects almost no light back across the vast dark gap. It only became findable in the final days, when it drew close to us. The survey that caught it had, in fact, imaged it a few nights earlier. Those earlier frames were recovered afterward, once its path was finally known. This is common, and astronomers call those recovered sightings precovery observations. They stretch the known arc backward and sharpen the orbit after the fact. Even so, the whole record of this rock spanned only about 5 days. 14 measurements over 5 days is a thin thread to hang an orbit on. Compare that thin thread to the 89 measurements gathered on this week's largest rock. A genuinely dramatic contrast. The gap between 5 days of data and 700 days of data is enormous. It is enough to say the rock missed, and missed by a wide margin. It is not enough to know that rock the way we know familiar ones. Contrast that briefly with how well we know a planet like Mars. Mars has been observed for centuries, mapped by dozens of spacecraft, walked by rovers. We know its gravity, its seasons, its dust storms, down to fine detail. A rock like 2026-OY, by comparison, is barely more than a rumour. 5 days of brightness measurements against centuries of planetary study is a staggering gap. And yet both objects obey the exact same laws of gravity and motion. The gap is not in the physics, only in how long we have been watching. And that thinness of knowledge is the quiet theme running under all 5 visitors. That picture is the reason I need you to meet the other 4 rocks. Each one of them teaches a slightly different lesson about the sky above you. One of them is large enough to level a city, and we tracked it for years. Another was seen for a single night years ago, and then lost completely. To understand why 5 quiet rocks matter, you have to meet the whole crowd. Part 2. 5 visitors, and the one we lost. Let me walk you through all 5 in order, because each carries its own warning. The first to arrive was an object called 2025 MB90. It reached its closest point in the small hours of the 19th of July. It passed at about 1.9 million kilometres, a little under 5 lunar distances. It was moving at roughly 9.5 kilometres every second through open space. This is the one rock in the crowd I want you to watch most closely. Of all 5 visitors, it is by a wide margin the largest object. Its brightness places its width somewhere between 40 and 90 metres across. Hold that size in your mind, because it has a terrible historical twin weighting. The year attached to that twin is 1908, and we will get there. Now for the reassuring half, and notice how fast a bigger loop follows it. 2025 MB90 was not a stranger who appeared without any warning. We first saw it back in June of 2024, more than a year ago. That first sighting came from one of the same automated surveys covered earlier tonight. It was a routine detection among hundreds that month, unremarkable at the time. Nobody watching that data stream in June of 2024 knew this rock's future role. It would simply be one line in a long, patient, growing catalogue of near-Earth objects. Only later, as its orbit was refined and its coming approach calculated, did it matter. That is how almost every object in this story begins, as one quiet line in a list. Astronomers have observed it 89 times across more than 700 days now. Its orbit is locked down, so its clean miss was certain well in advance. That is the system working at its very best, and it should reassure you. But here is the loop that should open the instant you exhale in relief. The largest, most dangerous rock in this week's crowd was also the best understood. Its size could flatten a city, yet we tracked it and never once worried. So the danger was never the big rock that we could see coming. Keep that strange inversion firmly in mind, because it will return tonight. The second and third visitors tell the same uneasy story as our opening rock. 2026 OZ passed on the afternoon of the 20th, that same busy day. It crossed at about 2.1 million kilometres, just over 5.5 lunar distances. Its size sits somewhere near 10 to 22 metres, a house-sized stone. Like our first rock, it was brand new, found essentially as it was leaving us. Then came the strange one, and I want you to slow right down for it. An object called 2020 OM made its pass on the 21st of July. The name itself tells you it was first discovered back in 2020, but here is the problem that makes this particular rock genuinely haunting. It was seen for exactly one single night, and then never found again. When you observe a rock for only one night, you can sketch its path roughly. The uncertainty wrapped around that path becomes enormous, and it never really shrinks. So when the models place 2020 OM near 9 lunar distances, they add a warning. The timing alone could be wrong by around 4 days in either direction. 4 days of uncertainty on a rock we glimpsed once and then lost. Let me be clear about what this is, and what it is not. Right now, 2020 OM is small, somewhere near 11 to 24 meters across. There was never any sign that it was heading for us on this pass. This is not a near miss that cost anyone any sleep, honestly, but it is the perfect portrait of a category that matters enormously. That category is the lost object, and there are a great many of them. We find a rock, hold it briefly, sketch its path, and then lose it. Every one of those lost rocks is a small hole in our map of the sky. 2020 OM is one visible hole among thousands we cannot even name yet. Remember that, because the holes in the map are where tonight is truly heading. I want to linger on the lost rock a moment longer, because it matters. Objects seen for a single night are not rare accidents in the record. They are a whole category, and the sky is quietly full of them. A survey catches a faint dot, measures it for hours, and then weather closes in. Or the object simply fades and moves on before anyone can follow up properly. And with only one night of data, the orbit can never be truly locked. The rock is not gone from space, of course, but it is gone from us. It becomes a prediction wrapped in days of uncertainty, like 2020 OM. Astronomers do try to recover these lost objects on later passes when they can. Sometimes a new detection is matched back to an old one-night sighting years later. But many are never seen again, and simply drift on, uncounted and unnamed. Each one shows that finding a rock once is not the same as tracking it. Holding onto an object, night after night, is its own separate and difficult problem. There is a term for objects that get lost, and then found again years later. Astronomers call it recovery, and it happens more often than you might expect. A rock glimpsed once in 2020 might be recovered, unexpectedly, in 2028. When that happens, the years of accumulated uncertainty collapse almost instantly into a solid orbit. It is one of the quiet, satisfying wins in this field, a lost thread finally rejoined. 2020 OM may well be recovered someday in exactly that fashion. Until then, it remains one small, patient gap in an otherwise growing map. The last of the 5 came a few days behind all the others. 2026 OU made its pass on the 23rd of July later that week. It crossed at about 3.7 million kilometers, roughly 9.5 lunar distances. It moved more slowly than the rest, near 6 kilometers every second. It too was a fresh discovery, caught by a survey telescope only days before arriving. Before moving on, it helps to name what all 5 rocks actually had in common. Every single one belongs to a broad family astronomers simply call near-Earth objects. That label covers any asteroid or comet whose orbit brings it close to ours. It is a wide net, and it catches everything from harmless dust to real hazards. So there is your crowd, 5 rocks carrying 5 separate lessons about our sky. One was large and known, one was lost and fuzzy, 3 arrived nearly unseen. Not a single one of them was a danger to you or to anyone else. And yet together they raise a question that writes itself inside your mind. If 3 of 5 were found days before passing, how many pass unseen? To answer that, you first have to see exactly how we hunt them. But first, one more thing about this particular crowd of 5 is worth noting. All 5 approach from roughly the same general direction in the sky. That is not a coincidence of danger, only a coincidence of orbital geometry that week. Rocks on similar paths around the Sun tend to arrive in loose clusters. Astronomers sometimes call these streams, though the term is used loosely here. It does not mean the rocks are related, only that their timing lined up. Understanding that clustering helps explain why some weeks feel busy and others feel quiet. Part 3. Why we only see them at the very last second. Most people picture the search for asteroids in completely the wrong way. They imagine one great telescope locked onto a single rock, tracking it like a camera. That is not how any of this actually works, not even slightly. The real thing looks far more like a lighthouse sweeping across a dark ocean. Its beam lights a patch of water, moves on and lights the next patch. A handful of survey telescopes, funded mostly by NASA, run that beam every clear night. They photograph enormous stretches of sky, over and over, hour after hour. Software then compares each new image against the last one taken. A star stays put between frames, and a planet drifts along a slow, predictable line. But a near-Earth asteroid, close and fast, leaps from one frame to the next. That leap across the frames is the signature that trips the alarm. 3 names do most of this patient work across the world's dark skies. Pan-STARRS watches from a mountaintop in Hawaii, high above the clouds. The Catalina Sky Survey scans from the mountains of southern Arizona. A system called ATLAS runs telescopes at several sites spread around the planet. Between them, they sweep the beam across the sky, night after night, endlessly. New facilities continue joining this network as funding and technology allow for expansion. Slowly and steadily, year after year. The lighthouse is not a fixed, finished thing, but a slowly growing constellation of instruments. Each of these surveys uses a specialized wide-field camera built for exactly this task. Pan-STARRS, for instance, uses a camera built from a grid of smaller detectors. Together they form a single sensor larger than almost any camera built before it. ATLAS takes a different approach, using several smaller, cheaper telescopes spread across sites. That spread lets it cover more of the sky more often, trading depth for speed. Each design reflects a different answer to the same underlying budget and physics trade. There is no single correct way to sweep a beam across a dark ocean. Stay with me, because the next part is where the lighthouse image starts to bite. When their software flags a new dot that moves like a near-Earth object, it gets posted. It goes onto a public list run by the Minor Planet Center, the world's clearing house. That posting is essentially a flare fired up into a global community of watchers. It says, "I found something moving, and I need help holding onto it tonight." Then a kind of relay race begins across the dark half of the planet. Observers everywhere, professionals and skilled amateurs alike, rush to point their telescopes at the candidate. They must catch it while it is still bright enough and close enough to measure. A candidate left unfollowed for a night or two can slip away and be lost. That is exactly how 2020 OM was lost back in 2020. Time zones themselves become a tool in this global relay of attention. As the object sets over one country, it is rising, dark, over another. The watch passes around the planet by longitude, hand to hand through the night. A great many people in that chain are not paid a single cent for it. They are hobbyists with serious telescopes, giving up sleep to help defend the planet. Only when enough measurements arrive, from enough places, can a real orbit be computed. Then the object earns its formal designation, the string of numbers and letters I keep reading, and only then can specialists run its path forward across the coming century for risk. That whole pipeline is fast, but notice the hard limit built into all of it. It finds things only when they brighten, and small rocks brighten only when close. Let me give you a number that shows how busy this quiet week truly was. From roughly the 17th to the 21st of July, the circulars poured out steadily. The Minor Planet Center issued something on the order of 40 separate new announcements. On a single night, the 20th, it put out around 15 of them alone. And its confirmation page, the waiting room for new candidates, held over 30 at once. Let me say that again, because it is far too easy to let it slide past. This was an ordinary, unremarkable July week, with no special alert, and no headlines. And still the sky-watching machinery logged dozens of new rocks and juggled 30 unconfirmed candidates. That is the baseline hum of our sky, not some rare and dramatic surge. The sky is not mostly empty with occasional visitors, as people tend to assume. There is a second system that works on a much shorter fuse than the rest. It is called Scout, and it watches the newest, still unconfirmed candidates closely. When a brand new dot appears and might be headed our way, Scout models it fast. It asks a blunt question: could this thing actually strike Earth within days? For almost every object, the answer comes back as a clear and reassuring no. But Scout exists precisely for the rare case where the answer is not no. It is the smoke detector wired to the fastest, closest part of the threat. And much of the follow-up that feeds these systems comes from unpaid volunteers. Skilled amateur astronomers around the world measure new candidates from their own backyards. Their positions flow into the same databases the professionals and specialists rely on. Some of these volunteer networks organise through online forums, sharing tips and comparing measurements. A newcomer can often learn the basics within a single evening of guided practice. The barrier to entry, once steep, has fallen sharply as software and cameras improved. A decent camera and a clear night are, for many candidates, genuinely enough to start. What once required a professional observatory now fits comfortably in a spare bedroom or backyard shed. Without that global volunteer effort, many faint candidates would simply be lost each night. The professional surveys find the rocks, but the crowd often helps hold them. There is even a formal outreach program built to welcome curious newcomers into this work. Citizen science platforms let ordinary people help classify asteroid images and flag possible detections. No advanced training is required to start contributing something genuinely useful to the search. Thousands of volunteers worldwide have logged hours doing exactly this kind of careful, patient sorting. It is a rare case where public curiosity translates directly into real scientific output. It is one of the few frontier sciences still open to dedicated amateurs. Some of these amateur observers have been doing this work for decades. Unpaid, a handful have their names attached to co-discoveries of objects now studied by NASA. It is a strange kind of fame, invisible to the wider public, deeply respected within the field. A retiree with a telescope in their backyard can genuinely contribute to planetary defense. Few other branches of modern science still offer that kind of direct, meaningful participation. It is worth remembering, next time you hear the word NASA, that the network is wider, spanning agencies, universities, and private observers alike. It includes government agencies, universities, and quiet enthusiasts checking the sky before bed. The sky is busy all the time, and we are only now learning to see it, and that raises the obvious uncomfortable problem hiding inside the lighthouse image. A beam that sweeps the ocean lights only the water it happens to touch. Everything between the sweeps, and everything the beam cannot reach, stays completely dark. So there must be a direction the beam simply cannot turn toward at all. There is such a direction, and it has already fooled us once before. It fooled us in a way that sent more than 1,000 people to hospital. That direction is the one place our lighthouse is physically forbidden to look, and to understand it, we have to travel to a cold morning over Russia. Part 4. The direction no telescope is allowed to look. Every telescope on the ground shares one single unbeatable enemy in the sky. That enemy is the sun, and its glare erases everything near it. You cannot point an optical survey telescope near the sun and expect to see rocks. The light simply drowns them, the same way noon erases the stars. The stars are still up there at midday, but the sky is far too bright. So there is a permanent wedge of sky centered on the sun that we cannot search. Any asteroid approaching Earth from that direction arrives out of the daytime glare, unseen. Our sweeping lighthouse beam has one whole quarter of the ocean it cannot light. This is not some rare theoretical weakness that engineers will quietly patch away. It is a hard physical hole in our defences, and it has a place name. That place name is Chelyabinsk, and the date was the 15th of February, 2013. Let me rebuild that morning for you as a physical event, not as old news. An asteroid about 20 meters across entered the atmosphere over the southern Ural region. It weighed somewhere in the neighborhood of 11,000 tons of rock and iron. It came in fast, at roughly 19 kilometers a second, on a low shallow angle. And it came in directly from the direction of the morning sun. Not a single telescope on Earth had it listed, because it hid inside the glare. Hold that fact tightly, because it is the entire reason this story matters tonight. The most watched sky in history missed a house-sized rock arriving from the one blind direction. It gave zero warning, none at all, right up until the flash. At an altitude near 30 kilometers, the air finally overwhelmed the incoming rock. The stone shattered and detonated in a single enormous airburst high above the ground. That blast released energy equal to roughly 440 to 500 kilotons of TNT. For comparison, the bomb that destroyed Hiroshima was around 15 kilotons of energy. So this was in the range of 30 Hiroshimas, released high in the morning air. Here is the detail from that morning that has never once left me. Most of the roughly 1,500 injured people were not hurt by the rock. They were hurt by their own windows, in the most human way imaginable. People saw the brilliant flash, far brighter than the sun, and walked to their windows. A minute or two later, the shockwave from that airburst finally reached the ground. It blew those windows inward, and the flying glass did nearly all the harm. More than 7,000 buildings were damaged across 6 cities in the region that day. Roughly 1,500 people needed medical care, overwhelmingly from that flying glass. I want you to hold that image, because it is tonight's whole lesson in miniature. The threat did not come from the direction anyone was actually watching, and the harm did not come from the part everyone was staring at. Both of those ideas are going to return tonight, each time much larger. Our opening rock this week was found because it approached through the night side. That was partly luck of geometry, nothing more heroic or clever than that. The very same rock, arriving a few months earlier, might have come from the sun. Same size, same speed, but a completely different warning, decided purely by timing. There is a haunting piece of the Chelyabinsk story worth adding here as well. That morning was captured on hundreds of car dashboard cameras across the region. Russian drivers routinely run those cameras, so the fireball was filmed from every angle. We have, as a result, the best documented major airburst in all of human history. The footage shows the flash, then the long, strange delay, then the shattering boom. That delay is the shockwave taking minutes to cross the distance to the ground. One large fragment survived the airburst and punched a hole in a frozen lake. Divers later pulled a chunk of it, over half a ton, from Lake Shabakol. And here is the fact that should sharpen the whole lesson for you. Chelyabinsk was the largest object known to strike Earth since Tunguska in 1908. More than a century passed between those two events, which sounds safely rare. But the gap is partly luck, since most such rocks burst over empty places. And the one that hurt people arrived, unseen, straight out of the morning glare. In the years since, Chelyabinsk has become a kind of touchstone for the field. Planetary defense conferences reference it constantly. Almost as a shorthand for the whole problem, it proved, in a single unmistakable morning, that the sunward blind spot was not theoretical. It showed regulators and funding bodies exactly what an unseen airburst over a city looks like. That single morning likely did more for planetary defense funding than a decade of warnings. Sometimes it takes a real, filmed, undeniable event to move a slow-moving bureaucracy. Chelyabinsk was that event, and its shadow still shapes how this field is funded today. So that is the blind spot, and for decades we had no real answer for it. Later tonight I will show you the machines being built right now to fix it. But before any solution, I have to clear up what these numbers actually mean, because a great deal of fear grows in the gap between a word and its meaning. And the word hazardous is about to surprise you, so stay right where you are. Part 5. Why the word hazardous does not mean what you fear. Let me clear up the vocabulary now, because the wrong words breed the wrong fear. You will often hear an asteroid's size given as one tidy, confident figure. That confidence is almost always false, and here is the reason why it is. When a survey finds a new rock, it does not measure the rock's size at all. What it actually measures is brightness, the amount of light coming back to us. And brightness depends on two separate things tangled together in one number. It depends on how big the rock is, and how reflective its surface happens to be. Picture a large lump of dark coal beside a small bright mirror in sunlight. From a great distance, both can shine back with exactly the same brightness. A big dark rock and a small pale rock look identical through a telescope. So astronomers report a size range, not a single number, and that honesty matters. They calculate the size assuming a dark surface, then assuming a bright one. There is a related instrument worth mentioning that helps refine these size estimates further. Radar telescopes, when an object passes close enough, can bounce signals directly off it. That returning echo gives a far more precise size and shape than brightness alone provides. Most of this week's rocks passed too far, or were too faint, for radar to help, but for closer, larger approaches, radar remains one of the sharpest tools available to astronomers. That is why every size I have given you tonight has been a span. Consider 40 to 90 meters, or 5 to 11 meters as examples. The range is not vagueness or hedging on the scientist's part at all. The range is simple honesty about what a single brightness reading can reveal. Hold that idea, because it explains why a rock's threat is never one clean number. Now let me handle the word hazardous, because it is a trap for the ear. Astronomers use a specific technical label, the potentially hazardous asteroid, with a strict definition. An object only earns that label when two separate conditions are both true. It has to be larger than about 140 meters across, and its orbit has to carry it within about 7.5 million kilometers of ours. Notice what that definition immediately does to this week's crowd of 5 rocks. Every single one of them fails the size test by a wide margin. Not one of them is, in the technical sense, a potentially hazardous asteroid. There is a related figure worth knowing, called the absolute magnitude cutoff. Objects brighter than about magnitude 22 are generally assumed to exceed 140 meters. That cutoff is how surveys triage thousands of detections without measuring every single one by hand. It is a shortcut, not a certainty, and it can be wrong in either direction. A very dark, very large rock can hide below that brightness threshold entirely. A small, unusually reflective rock can look brighter and larger than it truly is. So even the size categories carry a quiet margin of error built into them. When you read that phrase attached to some other rock in the news, remember this. It is a category about size and orbit, not a prediction that anything will hit. It is a watch list label, not a countdown to impact. And the difference is everything. Stay with me, because there are 2 more scales you should know by name. The first is called the Torino scale, and it runs from 0 to 10. It is built for the public, with 0 meaning no concern and 10 meaning certain catastrophe. The overwhelming majority of everything we have ever tracked sits quietly at 0. The second is the Palermo scale, a more mathematical tool for the specialists. It compares one object's risk against the ordinary background risk over the same span. You do not need the equations behind the Palermo scale to grasp its message. Everything passing this week sits at the bottom of both of those scales. That is where the vast, boring, reassuring majority of all objects live. And here comes the loop that keeps that reassurance from lulling you to sleep. Sitting at 0 only means an object's known orbit does not threaten us. It says nothing at all about the objects whose orbits we have never measured. There is one last piece of vocabulary, and it explains our lost rock from earlier. When astronomers describe how well they know an orbit, they use a condition code. It is a number from 0 to 9, where 0 is a beautifully certain orbit. 9 means the orbit is barely more than an educated guess in the dark. 2025 MB90, this week's largest rock, sits near the certain end. We have watched that large rock for years, so its path is nailed down. The fresh discoveries and the lost rock sit near the uncertain, guessing end. We caught them for only brief glimpses, so their paths stay fuzzy and provisional. That single number, the condition code, separates a confident prediction from a rough one. It is the difference between a precise minute and a 4-day window of uncertainty. It helps to have a real example of the Torino scale actually climbing. Back in 2004, an asteroid named Apophis was found and tracked. For a short, tense while, it reached level 4 on the Torino scale. That is the highest any object has ever been rated on that public scale. It briefly showed a small but real chance of striking Earth in 2029. Then, exactly as it should, more observations poured in and refined the orbit. The impact chance for 2029 collapsed to 0 as the path grew sharp. Apophis will now pass harmlessly, though remarkably close, in April of 2029. That is the pattern once again: fear from uncertainty, dissolved by more data. Every additional night of tracking shrinks the cloud of possible paths around a rock. A short arc gives a wide, frightening spread of where the object might go. A long arc collapses that spread down to a thin, confident, verifiable line. So the cure for a frightening new rock is almost always simply more looking. Contrast this with how uncertainty behaves in most other areas of daily life. A weather forecast 5 days out is often less reliable than one issued tomorrow. An asteroid orbit follows the opposite pattern in an important, reassuring way. Once an orbit is well determined, it stays well determined for decades or longer. Gravity is far more predictable than the atmosphere, which is chaotic and constantly shifting. That predictability is precisely why a well-observed rock like 2025 MB90 can be trusted completely. The physics does not change its mind the way weather does. There is a related public tool that lets anyone watch this process unfold. NASA and the European Space Agency both publish live risk lists on their websites. Anyone curious can see every object currently carrying a non-zero impact probability. Most entries sit at absurdly small odds, smaller than 1 in a million. A handful climb higher for a while, then usually drop again as data arrives. Watching that list update, night by night, is itself a small window into the system. It shows uncertainty shrinking in real time, which is a strange thing to witness. So let me gather the whole first hour into plain language before we turn. 5 rocks passed, all of them missed, and all of them were physically small. The largest was the best understood, and it was never once a genuine worry. The smaller ones were found late or known poorly, not through any negligence. That is simply the honest limit of what current tools can do for faint objects. None of that is the danger, and I told you so from the very first minute. So now I owe you the turn that the whole night has been promising. If the danger is not any of these 5 tracked rocks, then what is it? To answer that honestly, I have to take you back more than a century. I have to take you to a summer morning over an empty Siberian forest. Part 6. The morning 80 million trees fell. On the 30th of June, 1908, the sky over central Siberia tore open. It happened a little after 7 in the morning, above the Podkamennaya Tunguska River. And the very first strange thing about it is that there is no crater. That single absence is what makes Tunguska so unsettling and so instructive for us. An object came in fast and destroyed itself in the air, several kilometers up. It never touched the ground as a solid thing at any point. Instead, it converted itself, in one instant, into a wall of heat and pressure. That wall rolled outward across the forest in a vast, expanding ring of force. It flattened something like 2,000 square kilometers of dense Siberian woodland. The number of trees knocked down is estimated at around 80 million. They did not fall in a random scatter, and this detail matters enormously. They fell in a huge radial pattern, every trunk pointing away from the centre. Picture grass combed flat by an enormous invisible hand pressing down from above. A herder camped tens of kilometres away was reportedly thrown from where he sat. The blast knocked him unconscious, that far from the centre of the event. Windows shattered hundreds of kilometres away from the point of the explosion. Seismographs across Europe registered the concussion rolling through the body of the Earth. The energy released is estimated at somewhere between 10 and 15 megatons of TNT. Take the middle of that range and simply sit with the number for a moment. 10 megatons is roughly 1,000 times the energy of the Hiroshima bomb. 1,000 Hiroshimas, delivered in one silent flash over an empty northern forest. Now here is why I carried you all the way back to 1908. Remember the size of the Tunguska object, around 50 to 60 metres across. Now remember this week's largest visitor, 2025 MB90, at 40 to 90 metres. I asked you 2 parts ago to hold that size, and here is why. This week, a rock in the Tunguska size class passed our planet in the dark. It missed by 5 lunar distances, it was tracked for years, and it was harmless. But in raw physical terms, it belongs to the same family as the Tunguska object. The rock that could flatten a forest is not some rare once-in-an-age monster. It is a size of object that drifts past us, in some form, all the time. Let me be careful here, because this is exactly where comparisons get abused. I am not telling you that 2025 MB90 was a hidden threat. It was not, and its clean miss was known and certain well in advance. What I am telling you is something quieter and far more uncomfortable than that. The category of rock that levels a region is common, not exotic or rare. One such rock went past this week, and we happen to have it on a leash. So the real question is the one this whole night has been circling toward. How many rocks in that same Tunguska class are out there without a leash? And there is the turn I promised you, the twist under everything so far. The danger was never the rock with a name and a measured predicted orbit. A rock we can see and track and forecast is almost by definition not our killer. The danger is the other population entirely, the unlit and uncounted one. It is the Tunguska class rocks that carry no name and no orbit at all. They would arrive like Chelyabinsk did, with days of warning or none whatsoever. That is the real danger, not the 5 we watched, but the ones we did not. For nearly 20 years after 1908, almost no one investigated Tunguska. The region was remote and roadless, and the country was consumed by upheaval. It was not until 1927 that a scientist named Leonid Kulik reached it. Kulik would return to the site several more times over the following years. He remained convinced, for a while, that a large metallic meteorite must be buried somewhere. Expeditions searched for it using primitive metal detectors and careful ground surveys of the terrain. No such buried metal mass was ever found, which only deepened the mystery for decades. It was not until later scientific work confirmed the airburst explanation that the puzzle resolved. Kulik himself died in a prisoner of war camp during the Second World War. He never lived to see the full scientific understanding of the event he had first documented. Kulik expected to find a great crater and perhaps chunks of a fallen meteorite. Instead, he found something stranger that took him days to even make sense of. Mile after mile of forest lay flattened, the trunks all combed outward from a centre. But at that centre itself, the trees were stripped bare yet still standing upright. There was no crater anywhere, and there were no large meteorite fragments to collect. That absence is the signature of an airburst, an explosion in the air above. Modern researchers have used tree ring analysis from the region to help date the event precisely, matching growth patterns across a wide stretch of forest. The scarred, regrown forest still carries a faint chemical signature of that single violent morning. The object never landed, so it left scorched, standing trees where it detonated overhead, and it flattened everything around them where the expanding shockwave struck at an angle. Kulik's flattened forest is still, a century on, the clearest record we have. It shows exactly what a 50-metre rock does to the land beneath its airburst. Eyewitness accounts from villages near the blast add a human layer to the science. Farmers reported the sky splitting into two pieces, with fire crossing the northern horizon. Some described a heat so strong it felt like their shirts might catch flame. Windows shattered in a trading post at Vanavara, over 60 kilometres from the centre. A man there was reportedly thrown from his porch chair by the pressure wave. These accounts, gathered decades later from ageing survivors, remain the closest thing to testimony. They describe, in plain human language, exactly what the physics says should happen. And once you accept that the true hazard hides in what we cannot see, worse follows. Because a rock's size decides everything about what it does in our air. To understand why a 50-metre rock levels a forest, we need the physics. We need to follow one of these objects down through its final 100 kilometres. Part 7. What the sky does in its last 100 kilometres. Let me rebuild, physically, what happens when a rock actually meets our planet. Because the word impact hides an enormous amount of violent, specific physics inside it, and that physics is the whole reason a rock's size decides its fate. Start with a fact that feels wrong the first time you hear it. Our air, which parts around your hand, behaves like a solid wall to a rock. When an object moves at 15 or 20 or 60 kilometers a second, everything changes. The air in front of it cannot possibly get out of the way fast enough. So the air piles up, and it compresses, and compressed air grows ferociously hot. The rock is not mainly burning from friction, the way people usually say. It is being hammered by the pressure of the air it is slamming into. Scientists call that force ram pressure, and it builds on the rock's leading face. For a fast object, that pressure can climb past anything ordinary stone can survive. So picture the sequence unfolding across the last 100 kilometres above the ground. A rock tens of metres wide enters the top of the atmosphere at 20 kilometres a second. High up, where the air is thin, very little happens to it at first. Then it drops into thicker air, and the ram pressure on its face climbs. The surface heats to a blinding glow and begins stripping away in layers. And at some point the pressure on the front exceeds the strength holding the rock together. Now watch what the rock does, because the word for it sounds almost gentle. It flattens. It spreads sideways under the pressure, like dough pressed by a rolling pin. Scientists actually call this the pancake effect, and it runs away with itself fast. As the rock flattens, it presents even more surface to the oncoming wall of air. That raises the pressure further, which flattens it more, in a vicious closing loop. The rock disintegrates all at once, in a fraction of a single second. It dumps nearly all of its enormous motion energy straight into the air. That is an airburst, and it is exactly what happened over Tunguska and Chelyabinsk. Hold that rolling pin image, because the height of the burst decides everything below it. When a rock detonates high in the air, much of that energy spreads and fades. You get a shockwave, a flash, and broken windows, but the ground is partly spared. Chelyabinsk burst around 30 kilometers up, and that height is why people lived. Even releasing 30 Hiroshimas, that altitude turned a potential massacre into broken glass. Now lower the burst, and watch the same energy become something far worse. Take that identical blast and release it just 5 kilometers above a city instead. The shockwave arrives with far more of its full force still intact. That is the Tunguska geometry, a low burst over what happened to be empty forest. The only reason Tunguska is a scientific curiosity is where it happened to occur. It detonated over empty Siberian woodland instead of over a crowded capital city. That is the cruel lottery hidden inside every single one of these incoming objects. The same rock at the same speed gives wildly different outcomes on different days. The angle it enters at, the height it bursts at, and what lies beneath all matter. A 50-metre rock over the ocean is a footnote nobody outside science remembers. The identical rock over a city is a catastrophe with a real death toll. Nature does not aim at anything, and it does not spare anything on purpose. It simply rolls the dice, and raw geography decides the rest of the story. Now push the size up, past the point where our air can win the fight. Below a certain size, the atmosphere destroys the rock and you get an airburst. But above roughly 150 metres of solid stone, the air cannot stop it. The rock punches straight through and reaches the ground still carrying cosmic speed. It excavates a crater and throws out far more material than the object itself. This is the regime of the truly catastrophic impact, the ground strike, not the airburst. There is a useful middle case worth knowing between the airburst and the crater. Meteor Crater in Arizona was formed by an iron asteroid about 50 metres across. That impactor was dense enough and cohesive enough to survive most of its descent. It struck the desert around 50,000 years ago, carving a crater over a kilometre wide. The lesson is that composition matters as much as size in this ladder of consequence. A loose, stony rubble pile of the same size might have burst in the air instead. An iron rock of the same size might have punched straight through to the ground. Let me lay out the whole ladder of consequences now, rung by rung. At the very bottom sit the rocks a few metres across, like our opening visitor. Those are fireballs, brilliant streaks that scatter a few small meteorites and little else. They strike the Earth often, several times a year, usually over ocean or empty land. Climb to around 20 metres and you reach Chelyabinsk, 30 Hiroshimas and broken glass. Climb again to 50 metres and beyond, and you reach Tunguska itself. 1,000 Hiroshimas, 2,000 square kilometres of forest, a whole region erased. This is the city killer rung, and it is where this week's largest rock lived. It is also where a rock called 2024YR4 briefly lived last year. Keep climbing, past 140 metres, and you cross into formerly hazardous territory. A strike from a few hundred metres could release hundreds of millions of tons of energy. That could devastate not a single city, but an entire region around it. This is where the objects that keep planetary defence officers awake at night live. And then, at the very top, sits the rung that ended the age of dinosaurs. About 66 million years ago, a rock 10 to 15 kilometres wide struck Mexico. It carved a crater roughly 180 kilometres across into the Earth's crust. The energy is estimated near 100 million megatons of TNT, released in an instant. That is not 1,000 Hiroshimas or 1,000,000, but closer to 1,000,000,000 of them. It darkened the whole planet, collapsed the food chain, and killed 3/4 of all species. That is the top of the ladder, and it is what the largest impacts can do. Now step back and look at the shape of the entire ladder at once. This week's 5 rocks occupied only the bottom 3 rungs, and all of them missed. But the ladder does not stop at the rungs we happen to see this week. Here is the strange, hopeful twist buried inside all this fear, though. The giant dinosaur killers at the top are the rocks we have found best. Those enormous objects are bright and easy to see, and we have located almost all of them. None of the known giant asteroids is on a collision course with us. There is a helpful shorthand some scientists use for this exact situation, worth sharing. They call it the difference between a known unknown and an unknown unknown. The city killer population is a known unknown, since we know roughly how many exist. The rarest, largest impactors are closer to solved, since almost all have been found. The apocalypse from the sky we can very nearly rule out entirely. It is the middle rungs, the Tunguska-class city killers, that still hide in the dark. The regional catastrophe, not the extinction, is the danger still waiting to be mapped, and that gap in the middle of the ladder connects to something else entirely. Because our fragile world does not only face rocks falling out of the sky, on the very same nights these rocks passed, our own star was stirring. A doorway had opened on the face of the sun, aimed toward Earth. And to understand why that matters, we have to look up at daylight. Part 8. The night the wires caught fire. While those rocks slid past in the dark, our star was doing something unrelated. 93 million miles away, the sun had opened a doorway in its atmosphere. To see why that doorway matters, you first need its most extreme ancestor. So let me take you back to the 1st and 2nd of September, 1859. That is the night the sky itself reached down and set the wires on fire. On the morning of the 1st, an English astronomer named Richard Carrington was working. He was quietly sketching sunspots through his telescope, as he did most clear days. And then he saw 2 brilliant points of white light flare on the sun's face. Carrington was watching a solar flare erupt in real time, one of the first ever recorded. But he could not see the far larger thing the sun had just thrown off. Behind that flash, a vast cloud of magnetized plasma was hurled straight toward Earth. That cloud crossed the 93 million miles between the sun and us remarkably fast. It made the journey in about 17 hours, which is astonishingly quick for that gap. To cross that distance in that time, it moved near 2,000 kilometers a second. When it slammed into Earth's magnetic field, the whole sky lit up in response. Auroras, which normally stay penned near the poles, blazed down almost to the equator. People saw them over Cuba, over the Bahamas, over Hawaii, over Colombia and Mexico. In the Caribbean, people reportedly read newspapers by the light of the aurora at night. Miners in the Rocky Mountains woke and began cooking breakfast, sure that dawn had come. By every account, it was one of the most beautiful nights in human history, and it was tearing through the only electrical network the world had yet built. That network was the telegraph, the nervous system of the 19th century world. Across Europe and North America, telegraph systems convulsed under the storm's induced currents. The storm forced powerful electrical currents into the long telegraph wires everywhere. Those wires were never designed to carry anything remotely like that surge of power. Operators reported sparks leaping from their equipment as the currents poured through it. Some operators were shocked, and paper and recording tape caught fire in the offices. Then came one of the eeriest details in the whole history of space weather. Some operators found they could disconnect their batteries entirely and still send messages. They were running purely on the electric current the aurora itself pushed through the wires. For up to 2 hours, the sky itself was powering the telegraph network. Let me say that again, because the image deserves a second to truly land. The wires ran on the storm, with the batteries switched completely off. Now sit with the scale of that, and then drag it into our modern world. In 1859, the most advanced technology on Earth was a wire carrying dots. The storm set that single wire on fire across 2 whole continents. Today we have wrapped the entire planet in exactly that kind of long conductor. Continent-spanning power grids now stretch across every inhabited landmass on Earth. Pipelines, undersea cables and railway lines all run for thousands of kilometers. And a shell of satellites overhead handles our navigation, our timing and our communication. A Carrington-class storm striking that modern web would be a very different event. Some analyses estimate the damage in the trillions of dollars, not the millions. They warn it could knock out power to whole regions for extended periods. The reason is buried in the machines at the very heart of the grid. Those machines are enormous, custom-built, and cannot be quickly replaced once destroyed. Carrington was not the only person who saw the sun flare that morning. Another English astronomer, Richard Hodgson, independently witnessed the same brilliant white flash. 2 observers, at 2 locations, both caught the eruption in the very same minutes. That double sighting is part of why we trust the record so completely. The storm that followed pushed Earth's magnetic field to an extreme we can only estimate. By some reconstructions, it remains the most intense geomagnetic storm ever measured. And it was not merely a 19th century curiosity that cannot recur today. In July of 2012, a Carrington-class cloud of plasma erupted from the sun. It tore across Earth's orbit at tremendous speed, exactly the kind we fear most. But it crossed that orbit at a point where the Earth simply was not. We missed it by a matter of days in our journey around the Sun. Scientists studying it afterward were blunt that a direct hit would have been serious. We did not dodge that one through readiness, but through pure orbital luck. Researchers studying that near miss gave it a chilling nickname among themselves privately. They called it the storm that could have sent us back a century. Daniel Baker, a space scientist who studied the event, put it starkly in interviews. He said if that cloud had erupted 1 week earlier, we would still be picking up the pieces today. That kind of plain language from a working scientist is rare and worth remembering. It is not hype, because the physics behind the claim holds up under scrutiny. It is simply what a Carrington-class storm striking a modern grid would actually mean. Here is the reassurance, and notice the larger loop that opens right behind it. The storm heading for Earth this week was nothing remotely like Carrington. It was gentle, a minor disturbance, and nothing on the grid was ever at risk. But Carrington was not a freak event that can never possibly happen again. It sits at the top of the very same ladder whose bottom rung we touched this week. The Sun runs that whole ladder, from the harmless stream to the civilization-scale storm. And storms far smaller than Carrington have already reached down and hurt us badly. To see how, we do not have to imagine, because it already happened once. It happened on a March night in 1989 over the province of Quebec, and it dropped 6 million people into darkness in about 90 seconds flat. That is where we go next, because the mechanism behind it is the real warning. The beauty of the aurora and the failure of the grid share one hidden cause, and once you understand that cause, this week's gentle storm reads very differently. Stay with me, because the wires are about to stop being a 19th century story. Part 9. 90 seconds to darkness. Let me take you to the 13th of March, 1989, in Canada. A powerful geomagnetic storm struck the Earth in the small hours of that morning. It was nowhere near Carrington's scale, but it was severe in its own right, and it found the long transmission lines of the Hydro-Quebec power grid waiting. What happened next took less time than it takes to describe it to you. Currents induced deep in the ancient rock of the Canadian Shield surged upward. They poured into those long transmission lines stretched across the frozen landscape. At 2:44 in the morning, the vast electrical system began to fail, and it did not fail slowly, giving operators time to react and isolate it. In under 90 seconds, the entire Quebec grid collapsed into total darkness. About 6 million people lost power in the cold of a Quebec March night. They stayed in the dark for roughly 9 hours as engineers fought to restore it. Across the rest of the continent, more than 200 separate grid anomalies were logged. A large transformer was damaged as far away as New Jersey, thousands of kilometers off. Auroras from that same storm were seen far south, into Texas, Florida, and Cuba. David Bottler, a space weather scientist with Natural Resources Canada, put it plainly. He described that event as the biggest geomagnetic storm of the space age. And here is the part that should reset how you hear this week's gentle forecast. That Quebec storm was rated, in the long view, as a once-in-50-years event. It was not a once-in-a-century monster like the Carrington event was. So let me explain exactly how the Sun reaches down and does this to us. Understanding the mechanism is what turns a minor watch into something you respect. When a storm's magnetic field slams into and shakes the Earth's own field, currents flow. That shaking induces electric currents in anything long and conductive lying on the ground. Power lines, pipelines, railway signals, and undersea cables all become unwilling antennas. Scientists call these geomagnetically induced currents, and their key trait is crucial. They are direct currents, slow and steady, flowing into a grid built for alternating current. The grid simply does not know what to do with that kind of steady flow, and the piece of the grid that suffers most is the hardest one to replace. That piece is the transformer, and it is the beating heart of the whole network. The large transformers step voltage up and down as power moves across the network. A strong induced current pushes a transformer into a state engineers call saturation. In saturation, the transformer overheats, hums, vibrates, and can cook itself from the inside. That is what damaged the transformer in New Jersey during the Quebec storm itself. And here is the detail that makes a severe storm genuinely frightening for planners. The largest of these transformers are not sitting on a shelf somewhere ready. They are enormous, custom-built machines, often made to order over many long months. Sometimes a single one takes more than a year to build and to ship. Lose dozens of them in one severe storm across a continent and consider the result. You are no longer talking about a 9-hour blackout that ends by breakfast. You could be facing critical parts of a grid down for weeks or longer. Some utilities have begun stockpiling spare transformer parts, specifically against this scenario. Quietly, it is an expensive form of insurance, purchased against an event that may never come. But the alternative, waiting a year for a custom replacement mid-crisis, is far worse. A few spare units, warehoused quietly, can mean the difference between days and months of darkness. It is unglamorous logistics, the kind that never makes a headline, quietly protecting millions of homes. That is the scenario that appears in the serious studies of extreme space weather, and the grid is only the most dramatic of the vulnerabilities a storm creates. The same storms swell the upper atmosphere and drag on satellites in low orbit. They can nudge those satellites off track and corrupt the precise timing signals above. The GPS in your phone, in ships, in aircraft. It reaches the synchronized clocks that quietly run financial networks and power stations themselves. Severe storms also black out high-frequency radio, the fallback band for emergency services. So a great solar storm does not break just one thing in isolation. It leans all at once on the entire hidden layer that modern life sits upon. Let me give you the raw scale of what failed over Quebec that night. When the grid collapsed, it dropped roughly 21 gigawatts of power at once. That is the output of around 20 large power stations vanishing in seconds. The province went dark in the deep cold of a March pre-dawn hour. Engineers spent the next 9 hours carefully bringing the shattered system back online, and the damage reached far beyond Canada into the grid of the United States. That transformer harmed in New Jersey sat thousands of kilometers from the collapse itself. Afterward, Hydro-Quebec invested heavily to harden its network against the next great storm. The figure ran to around $2 billion Canadian of protective upgrades over time. That is the real cost of a storm, rated only once in 50 years. Now imagine the once-in-a-century storm, the true Carrington scale event, striking our modern grid. The studies that model it do not describe an inconvenience or a long weekend. They describe a slow, continent-scale emergency measured in weeks, not in hours. Modern grid operators are not blind to this risk, and they do plan for it quietly, year after year, without much public attention. Utilities now run geomagnetic storm drills alongside their more familiar hurricane and wildfire drills. Some transformers have been fitted with monitoring equipment that watches for the telltale saturation signs. Grid operators can, in principle, take vulnerable equipment offline before the worst of a storm hits. That kind of preemptive shutdown trades a brief planned outage for avoiding a much longer one. It requires accurate, timely forecasting from agencies like the Space Weather Prediction Center. The same watches and warnings that sound almost bureaucratic are, in practice, genuinely load-bearing. Behind every dry government bulletin sits a chain of decisions that can protect real infrastructure. That is worth remembering the next time a routine weather alert scrolls past on a screen. It is the electrical equivalent of boarding up windows before a hurricane makes landfall. The tools exist, but like the asteroid search, they only work if funded consistently. Now bring that mechanism back to this week's harmless little stream of solar wind. The storm this week was minor, and nothing on the grid was ever threatened, but it was the gentle end of the exact same force that emptied Quebec, and that force runs on its own schedule, entirely independent of the rocks, which raises a darker question about what happens when two clocks strike together. Imagine the day we finally spot an unseen Tunguska-class rock actually inbound. Now imagine that day happens to land during a severe geomagnetic storm as well. The power flickering, the satellites degraded, the GPS drifting, the radio washed out. The very tools we would need to track and warn and evacuate, all failing. That is not a forecast, but it is built entirely from things that are real. None of that happened this week, and I want to be completely clear about it. Nothing failed, and no rock threatened us, and the storm was gentle and minor. But the ingredients of a genuine emergency were all present, side by side, harmless, and the sky held one more thing that week, unrelated and strangely beautiful. Its parent is, by one honest measure, the most dangerous object we know. Part 10. The most dangerous, beautiful thing we know. Every August, the Earth drives through a river of debris left by a comet, and the sky fills with shooting stars we have named the Perseids. This year, that shower was already stirring on the very nights our rocks passed. It switched on around the 17th of July, quietly, in the late night sky. It will build, night after night, toward a peak on the 12th of August. The Perseids are the third thing that was happening in our sky this week, and they are the one thing you can walk outside your door and see. But I did not bring them here because they happen to be pretty. I brought them here because of what actually makes them, up in the dark. Their parent is a comet called 109P, Swift-Tuttle. And Swift-Tuttle is, by one specific and defensible measure, genuinely terrifying. It may be the single most dangerous object that humanity currently knows about. Let me justify that heavy claim, because it sounds like exactly the hype I avoid. Swift-Tuttle is a comet with a solid heart, a nucleus, about 26 kilometers across. The rocks passing this week were measured in meters, but this thing spans tens of kilometers. It is the largest object in the solar system that repeatedly passes near Earth's orbit. It swings around the Sun once every 133 years or so on its long path. Two astronomers, Lewis Swift and Horace Tuttle, independently found it back in 1862. Each time it passes, it lays down a fresh trail of dust and grit along its orbit. Its orbit and Earth's orbit very nearly intersect, which is why we cross that trail. Now I have to be careful and precise, because this is where fear gets abused. Swift-Tuttle is not going to hit us in your lifetime or your grandchildren's lifetime. When astronomers first refined its orbit, there was a brief flurry of real concern. Further observation cleared it up, as more data almost always does with these objects. The refined path shows no impact threat for at least the next 2,000 years. It will make a distant, harmless pass in the year 2126, well clear. The genuinely close encounters sit thousands of years out, around the year 4479, and even then, the impact probability is only something like 1 in a million. So why do I still call it the most dangerous object that we know? Because of what it would do if that improbable distant day ever actually came. Swift-Tuttle crosses our path at about 60 kilometers every single second of the encounter. Combine that ferocious speed with that 26-kilometer size and consider the energy. An impact would carry roughly 27 times the energy that killed the dinosaurs. Not 27% more energy, but 27 times the whole Chelyabinsk event. It is not the most likely object to hit us, but the most catastrophic we can name. Hold that distinction tightly, because it is the difference between understanding risk and fearing it. Most likely and most dangerous are two completely different questions about the same object, and here is the part of the Swift-Tuttle story that I honestly love the most. That same terrifying object gives us one of the gentlest gifts in the whole sky. Every August, the tiny pieces of Swift-Tuttle hit our air at 60 kilometers a second. Most of those pieces are no bigger than a single grain of ordinary sand. At an altitude near 97 kilometers, about 60 miles up, they meet the air. The friction of ramming through that air heats them past 3,000 degrees. They vaporize in a streak of light, and that bright streak is a single Perseid. The very physics that would make the parent an extinction event makes its dust beautiful. The speed that could end us, at grain of sand scale, simply writes light across the sky. This year's show is set up to be an unusually good one, too. The peak, on the 12th and 13th of August, falls almost exactly on a new moon. No moonlight means dark skies, and dark skies reveal the faint meteors a moon would drown. Under good conditions, the Perseids can produce around 100 meteors an hour. And there is a lovely coincidence stitched into that same new moon of August. On the 12th of August, that new moon passes directly in front of the sun. It casts a total solar eclipse across parts of Iceland, Spain and Portugal. The same alignment that darkens the sky for the meteors also blacks out the sun. The sky, when you actually watch it closely, is full of these quiet connections. Let me explain briefly how a meteor shower actually works, since it is elegant. A comet like Swift-Tuttle sheds dust and grit all along its long orbit. Over centuries, that debris spreads into a vast river stretched around the comet's path. The Earth crosses that same river at the same point every single year. So the Perseids arrive on schedule each August as we plough through the stream. The meteors all appear to shoot from one point, high in the constellation Perseids. That point is called the radiant, and it gives the shower its familiar name. The rate you hear quoted, around 100 an hour, is an idealized figure. It assumes perfectly dark skies and the radiant overhead, which rarely both happen. Real counts are lower, but the brightest Perseids leave glowing trails that linger, and every few years, a larger fragment produces a brilliant, slow-moving fireball. Those fireballs are chunks of a comet that has circled the sun for millennia. When you watch one streak over, you are watching ancient ice and dust burn. For anyone wanting to actually watch the Perseids, the practical advice is simple. Find a dark location, away from city lights, and give your eyes time to adjust. No telescope or binoculars are needed. Since meteors streak across a wide area of sky, the best viewing typically comes after midnight, once the radiant has climbed higher overhead. Patience matters more than equipment, since the show unfolds unpredictably, meteor by meteor. Some nights bring a rush of several in a few minutes, followed by a long lull. That unpredictability is part of what makes watching a real sky more compelling than any simulation. So there is the third clock, not a threat this week, but a standing reminder. Laid across our orbit in a trail of ancient comet dust is a lesson. The same forces that could destroy us are the ones that fill our sky. The Perseids are the friendly, gentle face of the exact hazard tonight is about, which leaves one obvious question hanging over everything I have told you so far. If the real danger is the rocks we cannot see, can we do anything? Are we simply sitting under this crowded sky and hoping the dice roll kindly? Or have we, at long last, actually started to fight back against it? The answer is that 4 years ago, we did something no species ever had. For the first time in the history of life, something living reached out and moved a world. Part 11. The day we moved a world on purpose. On the 26th of September 2022, we struck an asteroid on purpose. A NASA spacecraft about the size of a vending machine crashed into a distant rock. It hit at roughly 14,000 miles an hour, deliberately, by careful design. And in doing so, it changed that object's path around its companion body. The mission was called DART, and it is one of the most important things we have done. Let me rebuild it as a physical act, not as a line in a press release. There is a near-Earth asteroid called Didymos, orbited by a smaller body named Dimorphos. Dimorphos is a moonlet about 160 meters across, circling its larger parent. That pairing was chosen on purpose, because it offered a clean way to measure success. Dimorphos circled its parent on a regular, well-timed orbit of about 11 hours and 55 minutes. If you could change that orbit even slightly, you could measure the change precisely. You would simply time how the pair blocked each other's light as seen from Earth. It was a target with a built-in stopwatch, and that was the elegant genius of it. DART flew for 10 months across the solar system to reach that distant pair. In its final hours, it found tiny Dimorphos on its own using onboard cameras. Then it hit the moonlet head-on at about 6 kilometers every second. The impact was aimed to slow the little moon and tighten its orbit around Didymos. And it worked, but it worked far better than anyone had a right to expect. The plain physics of a vending machine hitting a mountain predicted about 7 minutes of change. That would have been counted as a clear and genuine success on its own. What actually happened was that the orbit shortened by a full 33 minutes. 33 minutes, not 7, and the reason for that gap is the whole point. The impact did not just transfer the spacecraft's own momentum into the rock. It blasted a huge plume of rock and dust off the surface of Dimorphos, and that ejected material, spraying into space, acted like a rocket exhaust pushing back. The debris roughly doubled to triple the shove the spacecraft alone could deliver. Ground-based telescopes watched Dimorphos in the weeks after impact, tracking its slowly changing shape. Some observations suggested the little moon had been reshaped, not just nudged in its orbit. A body once closer to round may have become noticeably more elongated from the strike. If that reshaping is confirmed by Hera, it tells us something new and important. It tells us that a kinetic impact does not just push a rubble pile, it can remold one. That distinction matters enormously for engineers designing a real future deflection mission. You cannot plan the perfect nudge without knowing whether your target will hold its shape. We did not just nudge the rock, we turned its own material into extra thrust. The orbit changed by more than 4 times what the raw collision would have produced. That was the first time humanity intentionally and measurably altered the motion of a celestial body. For hundreds of millions of years, the traffic between the sky and life ran one way. The sky acted, and life below simply absorbed whatever the sky happened to send. In September of 2022, for the very first time, life acted back. Nancy Chabot led the DART mission at the Johns Hopkins Applied Physics Laboratory. She is careful about what it did and did not prove. She has stressed that DART was a great and genuine demonstration of the idea, but she has also warned that we do not have such a mission ready to launch. In her words, we do not have that sitting around ready to go right now. Hold that sober line, because it is the hinge between hope and hard reality. We proved the principle works, but we have not built the machine for a real threat. DART did not fly entirely alone on its final approach to the asteroid. It carried a tiny Italian companion spacecraft, a CubeSat, released shortly before impact. That little craft flew past moments later to photograph the plume of debris. From Earth, telescopes and the Hubble captured the aftermath in startling, vivid detail. The impact blew out a tail of ejected material thousands of kilometers long. For a while, the little asteroid had a comet-like streak trailing behind it. Scientists gave that amplifying effect a name, the momentum enhancement factor. They label it with the Greek letter beta, and DART's beta ran high. It meant the debris carried away far more push than the spacecraft delivered alone. The impact itself happened about 11 million kilometers from Earth, in deep space, and the target was chosen as a binary precisely so we could measure it. Watching one rock circle another gave us the stopwatch to prove the nudge worked. That careful design is why DART is evidence, and not merely a hopeful gesture. Hera itself carries 2 small companion spacecraft, tiny CubeSats named Juventus and Milani. Juventus will attempt something no spacecraft has done before at an asteroid radar sounding. It will send radio waves into Dimorphos and listen for echoes from its buried interior. That data should reveal whether the little moon is solid rock or loose rubble throughout. Milani, meanwhile, will study the fine dust and mineral composition of the asteroid's surface. Together, the two small companions turn Hera from a single observer into a small fleet. That fleet approach, cheap companions riding along with a larger mission, is becoming standard practice. And the whole story is not finished, because a follow-up mission is already flying. The European Space Agency launched a spacecraft called Hera in October of 2024. It is crossing the solar system right now to return to that same asteroid pair. Hera's job is to survey the aftermath of the DART impact in fine detail. It will measure the little moon's mass and examine the crater that DART left behind. From that, scientists can pin down exactly how much the debris amplified the push. Right now, we only know that the debris roughly doubled the effect. Not precisely. Turning roughly into exactly is what makes deflection a real engineering tool. If you must deflect a real asteroid someday, you need that number before you launch. So we are not helpless under this sky, and that is the genuine good news tonight. We can move an asteroid, we have done it, and we are going back to measure it. But moving a rock is only one tool, and it is far from the gentlest one. There is a whole kit of ways to push a mountain through space, and every one of them teaches the same hard lesson about time. So let me open that toolbox for you, from the gentlest tool to the last resort. Part 12. 4 ways to push a mountain. The kinetic impact, the DART approach, is only one tool in the kit. Scientists have quietly designed a whole toolbox for moving a dangerous rock, and each tool tells you something about the single trade that governs everything. That trade is between how much warning we have and how gentle we can be. Let me walk you through the toolbox, from the gentlest option to the most desperate. The first alternative is the most patient and the most elegant of them all. It is called a gravity tractor, and the physics behind it is beautifully simple. You do not touch the asteroid at all, not with any impact whatsoever. You fly a heavy spacecraft alongside it and simply hold your position there. You stay close, station keeping beside the rock, for months or even years on end. The tiny mutual gravity between the spacecraft and the rock tugs on the asteroid. That feeble, endless pull nudges the rock, over time, onto a slightly new path. No impact, no explosion, no risk of shattering the object into dangerous fragments. Just gravity, patience and time, working together in the quiet dark of deep space. But the catch is right there in the description, and it is a serious one. It needs enormous lead time, years upon years, because the force is so small. A gravity tractor is a tool for a threat you saw coming a decade ahead. It is the gentlest option, and it is available only to the most prepared. Here is where I need the image that will carry the rest of this part. Think of deflection like nudging a boat's rudder far out at sea, not near harbour. A tiny push on the rudder, applied far from port, grows into a wide turn. The same tiny push applied at the harbour mouth does almost nothing at all. Every tool in this kit runs on that one principle of early, gentle steering. The gravity tractor is the smallest rudder nudge, applied the farthest from shore. It needs the longest runway of warning of any tool we possess. A second tool in the same gentle family is the ion beam shepherd. Here the spacecraft flies near the asteroid and points an ion engine at it. It sprays a stream of charged particles against the rock's surface, continuously. That gentle, steady push slowly alters the asteroid's momentum over a long span. Again, it is patient, precise and gentle, and again, it is hungry for time. These first two are the surgeon's tools, delicate and clean and slow. They work beautifully, but only if you find the patient many years early. Then there is the kinetic impactor, which is DART, the one tool we have proven. It sits in the middle of the kit, between the gentle tools and the desperate ones. It needs less lead time, because it delivers its whole push in a single instant. But it still needs years, because even a hard shove must have room to grow, and it carries a risk the gentle methods do not bring with them. Many asteroids are not solid stone, but loose piles of rubble held weakly together. Hit such a rock too hard, and you might not deflect it cleanly at all. You might instead fragment it, turning one trackable object into a spray of smaller ones. DART worked partly because scientists chose the target carefully and studied its structure. Against a real threat, that kind of understanding would be absolutely everything. And then, at the far end of the kit, sits the tool nobody wants. That tool is the nuclear option, and it is the tool of last resort. Films imagine blowing the asteroid to pieces, but that is not the serious concept. Shattering a large incoming rock at the last minute can make things far worse. It can turn a single bullet into a spreading blast of deadly buckshot. And that buckshot still hits the target, only now across a wider area. The serious idea is subtler, and it does not touch the asteroid directly. You detonate a device near the rock, not on it, off to one side. The burst of radiation flash heats one whole side of the asteroid's surface. That thin heated layer blows off, expanding into space as a plume of vapour. And that plume acts like a sudden rocket thrust, shoving the asteroid the other way. It is the most powerful method we can imagine, reserved for the true nightmare. That nightmare is the large rock found far too late for anything gentler to work. Look at the whole kit together, and one pattern governs every single tool inside it. Every method, from the gentle tractor to the desperate nuclear burst, needs lead time. There is a real mission already testing part of this toolkit in practice. In 2021, Japan's Hayabusa 2 returned samples from the asteroid Ryugu to Earth. That sample return mission was not a defense test, but it taught us something crucial. It taught us exactly how loosely bound a rubble pile asteroid surface can actually be. Engineers watching that touchdown saw pebbles scatter far more easily than models had predicted. That single observation quietly reshaped how planners think about hitting a real asteroid hard. A future kinetic impactor may need to be gentler than DART was, not harder. The more warning you have, the gentler and safer the tool you can choose. The less warning you have, the more violent and uncertain your only options become. And with no warning at all, you have no options left, and you are Chelyabinsk. There is real reason for hope inside this toolbox, and I want to honour it. The follow-up mission Hera is flying right now to measure our one real test. Ian Carnelli, who manages the Hera mission for the European Space Agency, has spoken of its purpose. He has framed it as part of humankind's shared effort to learn to protect our planet. That word shared matters, because this is not one nation's project, but a species-wide one. So we hold a kit full of tools, and every one of them works on time. But all that careful hope rests on a single fragile assumption underneath it. It assumes we actually see the rock coming, with years of warning, not days. And that assumption is exactly the one this whole week quietly called into question. Because the arithmetic of what we have found and what we have not is sobering. That arithmetic is where I have to take you next, and it is uncomfortable. It involves a number that the people who defend our planet say out loud. It is the number of city killers still hiding in the dark, uncounted, and it is far larger than most people would ever guess it could be. Stay with me, because this is the honest heart of the whole story. Part 13. The 15,000 nobody can find. Let me give you the true state of the search, in the plainest numbers available. Astronomers estimate about 25,000 near-Earth asteroids are large enough to be dangerous. These are the objects 140 meters and up, the city killers and worse. As of the most recent tallies, we have found roughly 11,000 of them. Now simply do that subtraction and let the remainder settle over you. It means we are somewhere near 40 to 45% of the way through. We have mapped less than half of the rocks most capable of erasing a region. So well over half of them, on the order of 14 to 15,000 objects, remain. 14 to 15,000 rocks, each big enough to destroy a city, are unfound. Their orbits are completely unknown to us, and we cannot name a single one. Let me say that again, because it is far too easy to let it slide by. These are not pebbles, and they are not the truck-sized rocks that burn up harmlessly. 15,000 objects, each large enough to devastate a region, are out there, and we do not currently know where a single one of them actually is. I want you to feel the weight of that number before we go any further. And these are not my words being dramatic for effect at your expense. In February of this year, at a major science meeting in Phoenix, someone said this plainly. Kelly Fast is NASA's acting planetary defense officer, and defending Earth is literally her job. She said there are an estimated 25,000 of these dangerous objects out there, and she said we are only about 40% of the way through finding them. Then she said the line that I honestly have not been able to shake since. It is worth understanding what her actual daily work involves, beyond that one quote. Kelly Fast helps coordinate observations across the global network of survey telescopes and follow up observers. She reviews new detections, tracks risk assessments, and communicates findings to the wider scientific community. It is detailed, unglamorous administrative and scientific work, done largely out of public view. The romantic image of planetary defense, dramatic launches and heroic last-minute saves is mostly fiction. The real version looks like careful data review, patient funding requests, and steady coordination. That quieter reality is in its own way more impressive than the fiction ever was. What keeps me up at night, she said, is the asteroids we do not know about. The person whose actual job is defending the planet fears the ones not on the list. She does not lie awake over the tracked rocks with their measured, predictable orbits. She lies awake over the uncounted ones, exactly the danger this whole night has circled. And it goes deeper than just finding them, because finding is only half the battle. Remember what Nancy Chabot said about our readiness to actually deflect a real threat. We do not have a deflection mission built and waiting in a garage somewhere. So the honest picture is neither helplessness nor safety, but something in between them. It is a race between how fast we can find and prepare, and how long we have. But here is the reassurance, and watch the larger loop that opens behind it. We do have a working system, and it proved itself just last year, in public. Let me tell you about a rock designated 2024 YR4. At the end of 2024, a telescope in Chile picked it up. And unlike this week's visitors, this one did not simply pass by and vanish. This one climbed onto the risk list and stayed there for a tense while. When astronomers ran its orbit forward, they found a real chance of impact. There was a genuine, non-trivial possibility it could strike Earth in December of 2032. Its impact probability climbed, over weeks of observation, above 1 full percent. It rose on the Torino scale to a value not seen for a serious object in years. Its estimated size, somewhere near 40 to 90 meters, put it in a familiar class. That is the Tunguska class again, the city killer rung of the ladder. For a while, it was formerly the most threatening asteroid on all the books. And then, something important happened, which is exactly why I am telling you this. As telescopes worldwide piled up more observations, the orbit grew sharper and sharper. That fuzzy cloud of possible future paths, the uncertainty around the rock, began to shrink, and as it shrank, the sliver of it that touched Earth got squeezed out entirely. The impact probability, which had climbed so alarmingly, collapsed back down towards zero. The rock came off the risk list, and the warning resolved, correctly, into a clean miss. Watch the shape of that, because it is a working defense system in real action. An object is found, and its uncertain orbit produces a real impact probability. The world's telescopes converge on it, and more data steadily refines its path. And the refined orbit either confirms the danger, giving years to act, or dissolves it. Either outcome is a victory, because either one replaces ignorance with knowledge in time. There is even a whole coordinated apparatus behind this that most people never hear about. There is an international asteroid warning network, a global agreement on who gets told. There are planetary defense offices at NASA and the European Space Agency for exactly this. They run practice drills, hypothetical impact scenarios played out step by careful step, so that if the real call ever comes, the response is not improvised in panic. We have quietly appointed ourselves a watch over the sky in a single generation, but that whole system caught 2024 YR4 for one crucial reason. It was big enough and bright enough to be found early and then followed. The system that handled it beautifully is the same system that gave us 4 days. 4 days on our small rock this week, because small rocks stay dark until close. The difference is not effort or funding, but simply light, and how much reaches us. So the whole enterprise comes down to seeing the small ones far earlier. It comes down to lighting up the dark ocean the lighthouse cannot yet reach. And that is not a fantasy or a distant dream that engineers merely hope for. Right now, 2 machines are being switched on that are built for exactly that. To finally see the 15,000, we are building entirely new kinds of eyes. Part 14. The eyes we are building right now. Remember the lighthouse sweeping its beam across a dark and enormous ocean. For 30 years we have been slowly building brighter and brighter beams, and 2 new machines are about to turn that beam into a floodlight. The first sits on a mountain in Chile, and its name is the Vera Rubin Observatory. It is a survey telescope on a completely different scale from anything before it. It is built to photograph the entire visible sky over and over with staggering sensitivity. In its very first stretch of operations this year, the results were startling. It discovered more than 11,000 new asteroids in just a matter of nights. That included dozens of new near-Earth objects found in that single early burst, and astronomers described it as the largest batch of asteroid discoveries submitted in a year. And here is the part that should genuinely change how you feel tonight. That flood of 11,000 rocks was only the warm-up, not the main event. Once Rubin is running at full stride, its reach becomes almost hard to imagine. It is expected to find on the order of 90,000 additional near-Earth objects. It should push our catalogue of dangerous city killers from under half toward roughly 70%. One single machine represents a generational leap in how much dark we can light. It is the brightest sweep of the lighthouse beam that humanity has ever built, but Rubin still watches invisible light, from the ground like all the others, and that means it still cannot look into the one forbidden direction, the sun. So the second machine is designed specifically to solve that exact blind spot. It is called Neo-Surveyor, and it is a NASA space telescope, not a ground one. It hunts asteroids not in visible light, but in infrared, in the heat they give off. That difference is the key that unlocks the direction we could never search, because it flies out to a vantage point away from the blinding earthbound glare. From there it can look closer to the sun than any ground telescope ever could. It stares into exactly that sunward wedge where Chelyabinsk hid until the final morning. It is aimed at launch no earlier than September of 2027, and NASA has already contracted a rocket to carry it up to that vantage point. Its goal is blunt and enormous, stated plainly by the people who built it. It aims to find at least 90% of dangerous near-Earth objects within a decade. Neo-Surveyor is, in a very real sense, the machine built to prevent another Chelyabinsk. It is the eye designed to watch the one direction our eyes have never seen. Let me give you a sense of the sheer machine that Rubin actually is. Its main mirror spans more than 8 meters across, gathering a flood of light. Behind it sits the largest digital camera ever built for astronomy, by far. That camera captures images of 3,200 megapixels in one shot. With it, Rubin can photograph the entire southern sky every few nights running. Night after night, it compares each new image against the last. Hunting for movement. That is the lighthouse beam widened into a floodlight sweeping the whole dark ocean. And Neo-Surveyor solves the other half of the problem, the sunward blind side. It works in infrared, sensing the heat a dark rock gives off, not reflected light. A charcoal black asteroid that hides invisible light still glows warmly in infrared. and from its vantage in space, it can stare far nearer the sun than we can. Between them, the two machines can light the ocean and pierce the glare. For the first time, both of our great blind spots have an answer coming. There is a third project worth naming alongside Rubin and Neo-Surveyor briefly. China has announced plans for its own dedicated near-Earth asteroid warning system. Still developing. A more complete global network spanning multiple countries and space agencies strengthens the whole effort. No single nation can watch the entire sky alone, given the Earth's constant rotation. International cooperation, quiet and largely unglamorous, is what actually closes gaps in coverage. The lighthouse beam gets brighter not through any one breakthrough, but through many contributing sources. Planetary defense, in that sense, may be one of the more genuinely cooperative fields in science. So the whole arc of tonight bends here, at last, towards something like hope. But it is an earned and narrow hope, not a comfortable or complete one. We have proven we can move a rock once as a careful experiment, and we are building the eyes to finally see the ones we have been missing. The window in which we stay mostly blind is, for the first time, closing. Let me be honest about the size of that window even so, right now. Today we still find city killers only after they are catalogued and studied, and we still find Tunguska class rocks only days before they slip past us. This very week proved that window is still wide open above our heads. 3 of 5 rocks were found only days ahead, exactly as it happened. A whole population of 15,000 city killers still sits unmapped in the dark. So the eyes are coming, but they are not fully open yet tonight, and that gap between the danger and our attention to it is the real subject, because a threat that is real but rare and delayed is one humans handle badly. We are about to leave the rocks and the sun for a moment. We are going to talk about the strangest vulnerability of all, which is us. It is the reason a danger this genuine can feel like no danger at all, and understanding that blind spot in ourselves matters as much as the one toward the sun. Part 15. Why this danger is so hard to feel. I want to give you the truest way to see everything from tonight. Think of the danger from the sky not as one threat, but as layers. Each layer operates on its own timescale, and each carries its own kind of blindness. There is the fast layer, the small rock found days ahead, or not at all. Against that layer, our only defense is better eyes, like Neo-Surveyor coming in 2027. There is the slow layer, the large rock findable years or decades in advance. Against that one, our defense is not eyes but action, the dart-style nudge applied early. And there is a third layer, which does not come from a rock at all. That layer is the sun, which can degrade the very machines the others depend on. 3 layers, 3 timescales, 3 different kinds of vulnerability, all real at once. And this week, remarkably, all 3 were visible together, in harmless form, overhead. That is exactly what made this quiet, uneventful week worth 2 hours of attention. Now here is the psychology that makes all of this so genuinely hard for us. Human beings are simply very bad at feeling risks shaped like this one. We are wired to fear the immediate and the vivid, the thing with teeth nearby. We are almost incapable of sustaining fear towards something real, but rare and delayed. Let me make that concrete with a comparison you can feel in your gut. If a plane had a 1% chance of crashing, you would never board it. 1% feels enormous when it is attached to something you can vividly picture. But a 1% chance of a city killer impact in some window barely registers. It is the same number, and yet a completely different feeling in your body. And that gap between the true risk and our felt concern is the deepest problem. Because here is what actually happens every single time, without fail, in the real world. A rock like 2024 YR4 rises on the risk list last year. For a few weeks there are headlines, and people pay real attention, and it feels urgent. Then, the orbit is refined, the probability drops, and the rock is cleared away, and everyone exhales in relief and immediately looks away from the whole subject. Which is entirely correct for that one specific rock, whose danger genuinely passed. But the looking away does not stop politely at the one rock that was cleared. The attention drains out of the entire subject. All at once, everywhere, the telescopes still need funding through all the long, quiet, uneventful years. The next mission, like NEO Surveyor in 2027, still needs building and launching. The map of the 15,000 still needs filling in, one dark night at a time. And all of that patient work must continue through the stretches when nobody is watching. That is the real vulnerability, and it is not a specific rock or a specific storm. And it is worth repeating precisely because it is so easy to forget. The vulnerability is the way our attention spikes at a scary headline and then collapses. The threat itself sits at a low, steady, patient level that never spikes or vanishes. The Quebec grid failed in 1989, and then the world mostly forgot about it. Chelyabinsk shattered windows in 2013, and the alarm faded within a single news cycle. The threat is constant, but human attention is not, and that gap is where disasters live. Every preventable catastrophe in history has lived inside that exact gap, without exception. This is not an argument for fear, and I want to be very plain about it. I have spent this whole night refusing to frighten you, telling you these rocks missed. The point is the opposite of fear, and it is simply sustained, informed attention. It is holding a steady gaze through the boring weeks, which are almost all the weeks. Because the boring weeks are precisely when the real work gets done, or does not. There is an old saying among emergency planners that fits this subject perfectly. The best disaster response is the one nobody ever has to actually use. A well-funded telescope that finds nothing dangerous for a decade is not a failure. It is the system succeeding quietly, finding rocks early enough that none of them ever frightened anyone. Success in planetary defense often looks exactly like nothing happening at all. That is a hard thing to keep funding, because nothing happening rarely makes headlines. And yet nothing happening, sustained for decades, is precisely the goal of the entire effort. The most dangerous moment in this whole subject is not the week a rock comes close. It is the long quiet stretch afterward, when everyone has stopped watching entirely. That is when the funding drifts, and the map stops filling, and the blindness creeps back. So the quiet of this week is not a reason to look away from it. There is a real history to how our attention on this has risen and fallen. In the late 1990s, a wave of films made asteroids briefly famous. Around the same time, the United States set a serious goal for the surveys. It asked them to find 90% of the largest kilometre-scale rocks nearby. That effort, sometimes called Space Guard, largely succeeded over the following decade or so. We found nearly all the true giants, and none was on a collision course. But then attention drifted, exactly as it always does once the fear recedes. The harder job, the smaller city killers, was left only partly done for years. Even now, more than 2,000 asteroids sit on the official hazard watch lists. Not one of them is predicted to strike us within the next 100 years. That is genuinely reassuring, and it is the fruit of decades of patient funding. But it was won during the quiet years, not during the brief public panics. The lesson is that steady, unglamorous work, not fear, is what actually protects us. Funding for this entire effort is, in the scheme of national budgets, remarkably small. NASA's planetary defense budget runs to a modest sum compared to most government programs. It is a fraction of what a single major weather satellite alone typically costs. That modest price tag protects the entire planet from a real, if statistically rare, hazard. Advocates within the field often point out how efficient that trade actually is. A relatively small, steady investment buys decades of advance warning against a civilization-scale risk, which is a genuinely remarkable return by any measure. Few government programs anywhere offer that kind of leverage for so little ongoing cost. The quiet is exactly the thing that has to be guarded and paid attention to. Which brings us, finally, to the week itself, seen whole as one single sequence. Because everything tonight was running at once over one small planet in a few nights. The rocks in the dark, the storm from the sun, the ancient comet dust burning. Let me lay that whole convergence out end to end and let you feel it. Part 16. The clocks that were all running at once. Let me walk you through the week as one single unfolding sequence of events. When you see it laid out in order, the word convergence stops being abstract. Start on the 19th of July, in the small hours of that morning. The largest rock, 2025 MB90, sweeps past at just under 5 lunar distances. It is tracked, known, and completely harmless, exactly as we established earlier. And on that very same day, high above your head, the sun is already active. Since the 17th, elevated electron flux has been washing through the satellite belt overhead. It is an invisible radiation stress on our spacecraft, switched on quietly in the background. Two very different pieces of the sky, a rock and a radiation bath, on one date, and far off, the first faint Perseids, the dust of Swift-Tuttle, have begun to streak. Move now to the 20th, which is the single most crowded day of all. In the late afternoon, the fresh Discovery 2026 OZ slips past overhead. A few hours later, at 36 minutes past 9 that evening, comes the closest pass. 2026 OY makes its nearest approach at 2.5 lunar distances, and it does so just 4 days after we first laid eyes on it. On that same day, on the face of the sun, the doorway finishes turning toward us. The coronal hole rotates across the centre of the solar disk, aiming its stream at Earth. The rock passes in the dark on one side of our spinning planet. The sun loads its slingshot of fast wind on the other side of us. Two clocks, wound on completely separate mechanisms, both ticking toward the same nights. Now come to the 21st and the 22nd, when the second clock strikes. The fast solar wind crosses the gap and reaches Earth's magnetic field late on the 21st. It drives the minor storm the forecasters had watched coming for days in advance. And threaded into that same window is the ghostly pass of 2020 OM. It slides by at its uncertain 9 lunar distances, inside a 4-day cloud of doubt. The storm we could see coming, and the rock we could barely see, arrive together. Then comes the 23rd, when the last of the 5 makes its pass. 2026 OU crosses at 9.5 lunar distances, another fresh discovery. And with that, the immediate crowd of rocks finally begins to thin out. But the Perseids do not thin, and instead they keep on building. They build night after night toward that peak on the 12th and 13th of August. That peak falls under a new moon, on the same day a total eclipse crosses. And in December, quietly, the Hera spacecraft arrives at the Dart impact site. It closes the loop on the one time our species ever fought back. That is the convergence, not one dramatic collision, but a whole system visibly running at once. Rocks in the dark, a storm from the sun, ancient comet dust burning overhead, a spacecraft closing on the site of our single act of planetary defense. Any one of these, on its own, is a footnote that few would remember. All of them, in 1 week, over one small planet, is a genuine portrait. It is what the sky truly looks like when you finally watch all of it together. Let me put a few hard numbers back on this convergence before it slips away. The satellite belt overhead had carried elevated radiation since the 17th of July. The forecast pushed the disturbance to a level of 5 on the geomagnetic index. That was enough to bring aurora to Seattle, to Edinburgh, and to Hobart in Tasmania. The closest rock, 2026 OY, passed at 2.5 lunar distances. The largest, 2025 MB90, passed at just under 5 lunar distances. The lost one, 2020 OM, slid by inside a 4-day cloud of doubt. None of those numbers on its own is remarkable or frightening in the slightest. It is only their arrival together, in one window, that makes the picture worth seeing. Consider, for a moment, how differently this week would have read as separate headlines. A small asteroid passes Earth safely, with no threat to anyone. A minor solar storm brings possible aurora to high latitudes overnight. A meteor shower begins its slow build toward next month's peak. A spacecraft continues its journey toward an asteroid, arriving this December. Each headline alone would earn, at most, a passing glance from a distracted reader. Strung together into one sequence, across one small planet, in one ordinary week, they become something else entirely. They become a portrait of a solar system that never actually stops moving around us. A single instrument reading is data, but a whole sky in motion is a portrait. Think, for a moment, about how rarely any of us actually look up. Most nights pass under a sky nobody in a given city bothers to observe. The rocks pass anyway, the sun flares anyway, the comet dust burns anyway, regardless. The universe does not require an audience to keep doing exactly what it does, but the difference between a watched sky and an unwatched one is not nothing. It is the difference between knowing what just missed you and never knowing at all. That difference is the entire reason a channel like this one exists tonight. It is not a large audience, measured against the scale of global media, but a smaller, steadily engaged audience, returning night after night, matters more than one viral spike. Attention that persists is worth more to this particular subject than attention that merely flares. If you have stayed this long, you are already part of that quieter, steadier group. That kind of attention, given freely on an ordinary night, is what this whole story has been about. And here is the thing I most need you to carry out of this week. None of it was dangerous, and that is exactly what makes it worth studying. Because the ordinary week teaches you what the extraordinary week will be built from. Every element of a real emergency was present this week, in miniature and harmless. The rock found too late to do anything but watch it recede into the dark, the storm degrading the very machines we would need in a genuine crisis. The Tunguska-sized class that once flattened 80 million trees in a morning, the blind spot toward the sun, and the vast gap of things still unfound. Remember the rolling pin, the way the air itself crushes a rock in its final descent. Every rock that misses is running that same gauntlet, just aimed a little wide. Now run that identical week again someday, but change only one single detail. Put one of the 15,000 unfound city killers where 2026 OY was, and put a Quebec scale storm where this week's gentle minor one happened to sit. You would have the exact day the Watchers have trained their whole careers for. This week was the fire drill, and its whole value is that nothing was burning. Which brings me back, at the very end, to the rock we started with tonight, and to the single question I asked you to hold 2 hours ago now. Let me close this out, because the rock has one last thing to leave with us. It is already gone, receding into the dark, and yet it is still here. It is still here inside the only question that ever really mattered tonight. Part 17. The rock that is already gone. At 36 minutes past 9, on the 20th of July, a rock passed Earth. It was the size of a truck, and it crossed at 2.5 lunar distances. We had found it just 4 days before, and then it was gone again. That is where I began tonight, and I asked you to hold one question. If we saw these rocks this late, what about the ones we never see? I told you at the start I could not answer that question, and I cannot. Nobody can, and that is not evasion, but the honest limit of what anyone knows. Yet I hope the question means something different to you now than it did before. This week, our sky was busy, far busier than most people ever pause to realise. Dozens of new rocks streamed past in the dark on an utterly ordinary week. For the small ones, we still get only days of warning, or none at all. There is still a wedge of sky toward the sun where we remain effectively blind. A Tunguska-class rock passed us this week on a leash, tracked and safe. And perhaps 15,000 more of that same dangerous class drift out there, unnamed. That is what the harmless rock left behind, once it had swept safely past us. So was this an ordinary week? Yes, it was completely and utterly ordinary. Not one dangerous thing actually happened to our planet across those several nights. And that, in the end, is the whole reason it was worth your evening. Because the ordinary week and the catastrophic week are built from the same parts. The same rocks, the same sun, the same blind spots, the same fragile grid below. The only difference is which rock, out of countless rocks, is on which path, and whether we happen to see that one in time to steer, or not. Remember the rudder, far out at sea, and the wide, gentle turn it buys. That turn only exists if we spot the rock while it is still distant. This week we saw them, and every single one of them missed us cleanly. 2026 OY is gone now, receding into the dark past the sun. It is heading back out toward the orbit of Mars, where it came from. It will not come near our world again for a very long time. It never once had any chance of harming a single person down here. It was, by every measure we have, nothing at all. A truck-sized rock. But it left one thing behind it, hanging in the dark above us. It reminded us we live on a small world, under an enormous, crowded sky. And that, for the first time in the long history of this planet, someone is watching. Someone is awake, keeping the count, filling in the map, one dark night after another. The rock is gone, but the ones we have not found yet are still coming. Consider what this means for the ordinary person listening tonight, far from any observatory. You do not need a telescope, a grant, or a science degree to be part of this. You can simply choose to remain informed, rather than tuning out after the fear fades. You can support the institutions that fund this quiet, unglamorous work through public will. You can be, in your own small way, one more person who keeps watching. That collective attention, spread across millions of ordinary people, is what sustains the whole system. The watch was never meant to be kept by a handful of specialists alone. The only question that matters is whether we will see the next one in time. Every clear night, somewhere on Earth, a telescope opens its shutter again. Somewhere, a tired volunteer checks one more faint, moving dot before going to bed. Somewhere, a specialist compares tonight's orbit against the one computed yesterday. Carefully, that is the whole apparatus, small and human and relentless, holding the watch. It has no dramatic headquarters, no glowing wall of screens, no countdown clock. It is a scattered handful of people who simply refuse to stop looking up. And the answer to tonight's question is still being written on clear nights right now.